Hello, everyone. This is Amir Abbas, and I am going to start this session now. And before I start the session, I will request those who are online to check if I am audible or not, and if there's any problem in listening to me. I'm going to fix that before we get started with the session. So, those of you who are listening this session live, can you help me to? Because I'm not sure whether I'm audible or not. What you can do is that if you can listen to me, you can write, I can listen you or whatever in the comments, and I will wait for that in a few seconds. I will wait a few seconds for that. Okay, I got confirmation somehow in a comment that I am able to, I'm, I'm audible. Therefore, in the interest of time, I'm going to jump directly into the session. And once again, first of all, I apologize for restarting these sessions late. It's been quite a while where I've not conducted these sessions, and I'm going to remind the viewers related to the format of this session. If you are watching this session live, you can ask me comments in the comment section, and I'm going to project that question of yours as like this on the screen, and I'm going to read that question, and I'm going to answer that question. So that is going to be one of the basics related to the interactivity of these sessions. But if you are not able to participate in the live session, that's also fine. You can ask me questions later on by writing a comment in the comment section of the recorded video. And the video will remain on the same link. Today we are going to be talking about modeling with the help of R, and we're going to be starting this discussion with the help of linear regression. Uh, for those of you who have just joined, I will request you, if you are not able to understand a specific point, to please ask me a question in the comments. And the way to do that, I'm going to repeat that because a number of people have just joined, is that you have to write the question in the comments, and I'm going to respond to that. So, in the interest of time, let's jump directly into this session. As I said, that the session is going to be talking. This is the last lecture in the series of sessions through which we are introducing R programming. And in these sessions, we have just gone very fast. We have talked about some basics related to R programming. We have talked about descriptive statistics related to R. We have talked about some statistical tests by using R. And today, through this very short session, we are going to introduce how to build model in R. These are not going to be an exhaustive content. I'm planning to as this is going to be the last session in the series of sessions which we have already started. I'm going to start another series very shortly, in a week or so, where we are going to be talking and taking each one of these topics in depth, and we'll be discussing these things in a lot of details. This is just a sensitizer to you so that you can get used to the R environment and get exposed to different terminologies. Okay, now about the topic. We are going to be talking about usage of model in R, and we are going to be using linear regression as an example. And just a few announcements before we jump into the topic is that I'm assuming that people who are viewing this session to have substantial understanding of what linear regression is, because uh, giving teaching linear regression is not going to be the objective of this session. Rather, the objective of this session is how to use R to formulate a linear regression model. So that is going to be clear. Therefore, I'm going to pass very quickly over the details where we, like the theoretical details related to linear regression, and I'm going to talk more about our code. So I'm going to move forward uh, with this, and I'm going to move towards the content of this presentation. And as I told you that I'm going to be giving a very brief introduction to linear regression, introduction to the data sets which I will be using for this specific demonstration. I'll, I will demonstrate some basic statistics uh, on the before going to the modeling. I'm going to talk about some basic descriptive statistics. Then I'm going to go into linear regression and its components. Also going to teach how to formulate regression diagnostic plots, and I'm going to teach you how to make your output prettier uh, and with the help of some of code. So this is going to be the outline of today's session. Uh, okay, so there is one question. How many previous sessions? Because I joined today. Just quickly to answer this question is that uh, we have had 3 sessions before this, and it's okay if you have joined today. I will recommend that you see this session till the end, and then if you go to my YouTube channel, there are all the recordings of all the previous sessions are there on the YouTube channel. So if you're interested, you can watch them all right from the beginning and then catch up later on this. Uh, but obviously up to you. That's what I would recommend. Okay, so talking about regression, what is regression first of all? Let me go to the next slide. And this is all we are going to be talking about, the theoretical details related to linear regression. When I meant when I talked about regression, I meant linear regression. So this is all of the theoretical details which I'll be talking about linear regression. As I'm assuming that those who are attending this session will already have a substantial understanding of what linear regression is. So linear regression is a linear approach for modeling the relationship between the scalar response variable and one or more of the explanatory variables. Um, there are 2 types of linear regression. One is simple linear regression, in which there is one explanatory variable and one outcome variable. And there is multiple linear regression and more than one explanatory variable, and definitely obviously one response variable is there. Uh, Okay, so as I said, this is all of the theoretical details which I will be talking about today, and I'm going to, as I said, that the objective of this session is to walk you through the code which has been, which you can use to formulate a linear regression model. So I'm directly jumping into the code. So here is the code, and as you know that whenever we start coding in R, first of all we load the important libraries which we'll be interested in. So these are the libraries which I will be interested in. So I'm going to load these libraries, and these are loaded, and then I'm going to go straight into this data set, which is known as, the name of the data set is Boston. And if I want to just see this data set, you know that there is a function in R which is known as set, and you put in the name of that data set as an argument in the function head. You will be able to see the first 6 rows of your data set, and the columns, all of the columns will appear, and if the columns are greater than the amount of space which is present on your screen, you can use this small arrow to see whatever other columns are there. And as you can see that there are 6 rows of 13 columns. But what I want to do, I want to understand the structure of the data in a better way. So there is another function which is known as str, and I use the str function and use the name of the data set as the argument inside the str function. And what this function is going to do is going to give me the details of individual variables in the data frame, meaning that what is the type of the variable, and give me a glance of whatever is inside the variables. It's also going to give me the number of observations which are there in the data set and the number of variables which are present in the data set. But here I do not know because I just got exposed to this Boston data set. I do not know, okay, what is RAD? Okay, what is CHAS? These are all acronyms or short names for the names of the variables, and I'm not sure what they do. So for those data sets which are with some of the R packages, or are present in base R, what you can do is use a simple trick to find out what is there inside this data set, which is that you put in a question mark and write the name of the data set and then run this simple line of code. Now what is going to happen is that if you see on this side, something is going to appear. uh, it's a link has appeared which is talking about the Boston data. Okay, and I'm going to click on this link, and you can see that it's saying that Boston data is the part of this ISLR2 package which we just loaded. Okay, so there is a comment which is saying that text on screen is not visible. Let me see what I can do for this. Okay, let me see. Okay, so I hope this makes it better. Next time I will try to make it a bit bigger. In the interest of time, I'm not going to mess up with the font size at this stage. Okay, I'm assuming that you're, for those of you who cannot see the text on the screen, I will request you to use laptop to watch these sessions rather than using your mobile phone, because codes can be non-readable on the mobile phones. Uh, that's what I can say right now. But you will do some part. I will do some part to make these sessions more comprehensible in terms of the text size which are concerned. Okay, so this is the Boston data, and as I said, that this is the part of ISLR2 package. Um, and you can see, okay, you what we were talking about is some of the description of this data set. And we can see that the data set, and this data has a description which is that a data set containing housing values in 506 suburbs of Boston. Okay, and these are the details of variables. For example, we uh, we can see that CRIM is per capita crime rate by town, ZN is the proportion of residential land zone for lots over 25,000 square foot, and so on and so on. And you can see what each and every variable means, and we will be using this as our guideline whenever we are stuck uh, in terms of the interpretation of these data sets, that which variable means what. And if you want to use it as it, there is a reference for this data set as well. You have to cite it, and there is an example code of where this data set has been used as well. So this gives you some overview about what the data is about. If there is any data which is part of any of the R package, or it's part of the base R, you can just type question mark and the name of that data set, and you will hopefully get similar details for these data sets. So what we are going to do right now, we are going to directly jump into some descriptive statistics. And by descriptive statistics, we mean that, okay, all of you know that before we do not run into modeling straightforward. What we do is that mostly we draw some graphs, we run a few descriptive statistics. So right now what I'm interested in is I'm interested in finding out the variables which are able to predict the median value of owners occupied homes in $1,000, which is represented by this variable called MEDV. Okay, and I'm going to see the relationship of this MEDV variable with other variables. So first of all, I'm going to see how MEDV is predicted by LSTAT, which is the lower status of population in terms of percentages. And I'm going to draw a scatter plot. And a scatter plot can be drawn with one of this function, which is known as qplot function. And the way qplot function works is that you first of all put in the x-axis variable as an argument, then the y-axis variable, then you put given the data which you want to use for this scatter plot. This portion of the code will give you the scatter plot, but what I want to do is I want to label the x and y axis as well. So I'm giving an interpretable x-axis label, an interpretable y-axis label, and an interpretable title for this plot as well. And I'm going to run this code. Okay, and it's going to take a while. And if you can see that there is a negative uh, relationship, there is a negative correlation between median value of owners occupied homes in 1000 and the lower status of the population percent. Uh, and we can use this relationship in a model and to find out how the linear regression will function, will work out in this between these two variables, where we want to predict MEDV with the help of LSTAT variable. In the same way, just to demonstrate, oh no, I have not used any other scatter plot. So this was just to demonstrate one of the scatter plot. We can draw with the help of uh, similarly, you can draw other scatter plots as well, using other quantitative variables, or if you have qualitative variables, you can draw box plots for the levels of the qualitative or categorical variables, to find out how the dependent variable varies across the levels of the qualitative variable. But that's what I've not done here. What I've done here is I've jumped directly into a linear regression model, and how to formulate a linear regression model. And the linear regression model can be run with the help of this function, which is known as lm. And what it does is that, first of all, okay, what is your dependent variable? We discussed that MEDV, variable name MEDV, which stands for median value of the owner occupied homes in 1000, that is going to be our dependent variable. And now at this stage, I just want to choose one of the variable, which is lstat. And the next argument is going to be data equal to whatever the name of the data is. And I'm just going to run this line of code. And what this is going to do is going to run a linear regression model, where the dependent variable is MEDV, the independent variable is one variable, which is lstat, and the data is Boston. It's going to take MEDV and lstat from the Boston data frame and is going to run a linear regression model on it. And it's going to be saved to an object which is known as lmfit. I've named as lmfit. You can name it whatever you want. And I'm going to show this lmfit data, this object, and this is what it is showing. It's showing the formula which you used, and it is showing the intercept and the coefficient of the lstat. That's all that it is showing over here. uh, so what I'm going to do right now, now this is kind of weird, because when you just print out this lmfit variable, or whatever, to whatever variable you have saved your linear regression model to, it's going to give you a very simple output. But if I find out the summary, use the summary function and put in the name of the object of the linear regression model, I get a lot of more details, right? I'm going to talk about these details in a bit, but first of all, let's see what is actually contained in this object lm.fit, right? So I'm going to use a function which is known as attributes, and I'm going to take lm.fit as an argument. And okay, so these are the attributes, which means this lm.fit contains coefficients, it contains residuals, and is contain many of these things, which means that if I want to, what I want to do is, if I use this lm.fit object and use the dollar sign and choose the first component of this lm.fit object, I'm going to get the coefficients. Okay. In other words, if I'm just interested in coefficients from this object, I'm going to use this line of code, right? So I'm going to do something very simple, but uh, it may sound weird, but you have to do it the way I'm saying you to do, and it will become clear why I'm saying it in a bit. But what I'm going to do, I'm going to take the summary of lm.fit object, and I'm going to save it in another variable which is known as lm.fit underscore summary. You can again save it in you can name it whatever you want. I'm just naming it lm.fit underscore summary, right? Okay, and so what I'm going to do is I'm going to find out what are the elements which are contained within the object lm.fit underscore summary, and it will give me if I run the function names and with the argument as lm.fit underscore summary. These are the objects which are contained inside the, uh, these are the elements which are contained inside the object lm.fit underscore summary. Okay. So what I'm going to do is that I'm going to, I'm only interested in coefficients from this summary linear regression model object. And I'm going to just print that out and to show you how it looks like. Now you will see that, okay, there is a lot of important details which have been spelled out in which you're interested. For example, you will be interested in standard error, the t-test, and the p-value, and the absolute value of the coefficient, and the value of the intercept as well, right? At this stage, you can see that they have been not rounded off, which means that they have a number of decimal places. What I want to do is that I want to round it off to say 3 decimal places, and what I can do is I can take the whole of this code and put it inside the round function as one of the argument. The whole of this line has been put over here, and I'm going to the second argument is going to be the digit 3, which is I'm telling the round function that, okay, take whatever is in the columns, the digits inside these columns, and round it off to 3 digits. Okay, so when I run this, I get a very beautifully rounded off, automatically rounded off output to 3 digits only. You can see this p-value values have been rounded off to 0, because you know that p-value can be if you can see over here that they are the p-value is very low, and that have been rounded off to 0. And if you want, I will show you later on as well how, if you choose, you can choose not to round them off to uh, uh, or you can choose, or you may not choose. It's up to you, whatever you want. But this is one of the option with the help of which you can you can round off the variables. So far, I am hoping that those of you who are online are understanding it. And as a reminder, if you are not able to understand, you can ask me questions by asking questions in the comment, and I will continue with the session. Okay, so we have made a linear regression model, and now we want to understand how good or bad that linear regression model is, right? Uh, so there are a few ways which we can do it, and I'm going to make a few plots. Okay, so what I'm going to do, I'm going to run this piece of code, and let me explain what I did. Is this first line of code, what I'm telling R, then okay, this part function is going to tell R that, okay, make these graphs uh, in 2 rows. Okay, this is the first row and this is the second row, and and this plot is the function, and I'm going to use the lm.fit object which is originally used. Let me show it over here. So lm.fit is the object which was created um, after the linear regression model was originally run, right? I'm going to use this lm.fit object as an argument inside the plot function, and I'm going to run this code, and I'm going to get these 4 plots, which I'm going to use to interpret that how good or bad our linear regression model is. I will give you a few seconds to see uh, this these graphs, and figure out if you can find out how good or bad our linear regression model is. So these graphs are used to understand and to interpret how good or not good the assumptions related to the linear regression model are. And we are going to comment on each one of them very briefly. The first one of the graph is residual versus fitted when a linear regression model is formulated. This is one of the graph which we draw in order to interpret. And what this shows is that as you can see that on x-axis there are fitted values, and y-axis there are residuals. And what we want to see is that residuals will have a constant variance when plotted against the fitted values, which means that you can see that in here the variability is changing, but we will have want to have the variability to be constant across these. And the residuals and fitted value will be uncorrelated, so we can see that they are not correlated, but there is some variance of the variance of the residual across the fitted values varies. So that is something which we can observe related to this graph. The second graph is a QQ plot, which is used to find out the how good whether the standardized residuals are normally distributed or not. Okay, and we can see that we can use a linear model for prediction if the underlying normality assumptions don't hold. However, in order for the p-values to be believable, the residuals from the regression must look approximately normally distributed. So you can see that they are not completely normally distributed. As you can see that they deviate from the normality over here. But yeah, I mean you can comment on the normality of the residuals with help of this graph. The third graph is known as scale plot, and this is another version of the residual versus fitted. There should be no discernible trends in this graph. And the fourth graph is talking about leverage. Is showing the leverage versus residuals, and leverage is a measure of how much an observation is influenced, how much an observation has influenced the model. It's a one number summary of how different the model fit would be if the given observations were excluded compared to the fitted model where the observations are included. Points with high residuals and high leverage are outliers. They are skewing the model fit away from the rest of the data and don't really seem to fit with the rest of the data. So we are going to be observing where there is a outlier in the data or not, and just if you want to go into further details related to this point, I've put in the source of this text in here as a reference, and I will be sharing this code through our WhatsApp group as well, so you can go on later on as well and see it and explore it if you want to. I'm going to move further, and so far we have just used a simple linear regression model where there was one explanatory variable and there were one outcome variable. How if you want to do the same thing where there's obviously one outcome variable with a number of explanatory variables? The same concept is going to apply. If you understood what I taught till now, you can easily replicate this process with very small modification, and you can use a multiple linear regression model. And the way to do that is okay, so what we did is that now what we want to do is we want to predict this MEDV data set, this MEDV variable. And what I want to do is I want to use all the other variables in the data set, which means age, which means RM, NOx, DIS, etc., all the variables in this Boston data set to predict MEDV variable. And that is possible if, so I use the same code. If just let me show the code which I previously used. In fact, let me copy that and paste it just along with it so that you can see the difference and develop onto that on the basis of that, right? So this was the original code, and this the one which is selected right now. This was the code. Oh, I'm sorry, I just forgot to put it full screen. Okay, so what I was saying is that I've just copied the code from the previous part where I just use one dependent variable and one independent variable, and I'm just copied that portion of the code, and now I'm going to use the same code to make to adopt the same code to make predictive model, linear regression model, where the dependent variable is going to be MEDV, and I'm using all other variables in the data set to predict MEDV. And what I'm going to do initially, what I was using this tilde symbol, and then the name of the variable which I'm using to predict. But here, what I'm going to do is I'm going to use tilde and just a dot. This dot is going to tell that, okay, use all the data, all the variables inside the data Boston data set except MED variable, and construct a linear regression model and save it to this object lm.fit_all. I hope this step is clear. If it is not clear, please stop me and ask questions by commenting in the comments. I'm going to run this and it will be saved into the document lm.fit_all. What I'm going to do, as I demonstrated previously, I'm going to take this lm.fit_all and save it into the summary. I find out the summary of this and save it into the summary object, and I'm going to run this code. And then finally, I'm going to take the coefficients from this summary object and round the coefficients to 3 decimal places. So what I've demonstrated previously, I've just done it quite quickly without a lot of explanation, because I've already explained that previously. And as you can see right now is that all of the variables have been included in our model, including LSTAT, which was previously included, and all other variables, their estimates, standard errors of the estimates for the coefficients are there. And then what you can see is that there's a t value over here, value of the t statistic for each coefficient is there, and the p-value is also there. Okay, so in the same way as we discussed, we can run the diagnostic plots for this model as well. The code is exactly the same, with object lm.fit_all, which was the which was this particular object, as which was formulated as a result of lm function, being where MEDV was the dependent variable and all of the variables were the independent variables. And you can interpret these graphs on the basis of the instructions which were given previously. And finally, there's one last point before I end this session, is that uh, if you want to, okay, this is also good, but if you want to improve the way your output is being shown on the screen over here, or like you want to show it like this, or you want to improve the way it is being shown in the document in which you save, or in the HTML file which you are going to knit as a result of this presentation, you can use this cable function, and you can put in the lm.fit_all_summary object and take out the coefficients from that. And this argument, which is digits with this vector 3344, which, and that is, these digits are telling the cable function that round the first, okay, this 3 is telling it to round the first column into 3 decimal places, the second into 3 decimal places, the third into 3 decimal places, and the fourth one into 4 decimal places. So with the help of this function, what you can do is that you can also control each that to which how many number of decimal places each column are required to be round it up. And if you run it over here, it is going to give a better looking table. And if you knit it, it's going to even look much better over here, which I have not knitted over here right now. So I think this was a very short session as compared to our previous session. I just wanted to touch base again, because we have not interacted for quite a while, and I just wanted to restart these sessions. I'm anticipating that we'll be running these sessions quite regularly. How regularly I'm going to do that, I'm going to announce them in a few days. But I would request you, to all of those who are watching this session live, and to all of those who will be watching the recording of these sessions, to please give me feedback on these sessions, because this feedback helps me to improve these sessions. And and there is a question. Okay, so there's a question from Salima, and she is asking about so she has Salima is asking to let me read her question, and please, if you can brief par one more time. So let me let me show you, if you do not run par, what is going to do, and you will understand what. So I'm going to, because I've already loaded the the model, so I'm going to just run this line of code only. Okay, and what is going to happen that each, so there are four graphs, and each one of the graph is getting loaded separately, which means that you have to click and toggle around between different pages. I mean, there are four graphs, there are four pages, right? That's one way to do. I mean, that there's nothing wrong in that, but I wanted that all of these graphs should show in one page, and I'm going to use is this the par function with this argument as mf row, and giving it a vector of 2 and 2. And what it's going to do is going to structure the graphs as an output as one. I mean, this is just one picture. If you just export it in another way, all of these four graphs, they have been organized in a single picture. So that's how you can make multiple graphs. You can print them on separate pages as well if you want to, but if you want the information to be condensed, you have issues related to space when you're making a publication in a manuscript, or there are limitations, space limitations by different journals. Then this is one way, this is one function which will become handy in organizing your visuals. I will recommend that you Google this power function. You will come across a number of other variants of it as well. So MF. So the next question is, what is MF in this? MF means that the number of rows. So okay, the total number of graphs are 2. I'm going to organize these graphs in 2 rows, which means, okay, the first row will contain the 2 of these graphs, and the second row will contain the 2 of these graphs. And as if I'm not mistaken, I have to recheck, but you can also give the information in the terms to this function in the form of rows or in the form of columns, that how many columns should be there and how many rows should be there. I am hoping that this is clear, but if it is still not clear, please ask me again, and I'm going to be I'm here to answer questions if you have any, if it's still not clear. Any good book related to our programming? That's a very good question, and I'm going to that has a question. Ryan, you have asked a very pertinent question. So there is a separate series which I've already started, and I've released one of the videos, only the first video to that. What I will do is in the next video of that series, which will have 10 minutes recorded video, I'm going to talk about the recommended textbook for beginners related to art. But the short answer to that is, there are many books. To be honest, I do not exactly know which one to recommend it to you right now. I will answer this question hopefully in the next video. Okay. Sanima says thank you. And with this, for those of you who have not yet subscribed to my YouTube channel, I will recommend that please subscribe to the YouTube channel. And I'm really thankful to those of you who have taken out their time to watch these sessions live. It really helps me to make these sessions interactive, and I will be also hoping from those who will be watching the recording in the sessions that they will share their feedback with me. With this, I will say bye for the night. Take care. Allah Hafiz. Bye.